Hi everyone, welcome to an inspiring session of modulyss Talks. I'm Amandine, your host for today's webinar. For people new to this session, with our modulyss Talks, we try to educate and inform the design industry experts. And today is our first webinar of the year. This time we will talk about acoustics, but now with a focus on commercial spaces and how that has an impact on flooring. We have Kyriakos with us. He will talk about how to optimize the acoustics in a workspace environment. Kyriakos is the founder of acoustic consultancy agency KP Acoustics, and I will give the word to him.
Thank you, Amandine. Thank you so much. Hi, everyone. My name is Kyros, Managing Director and Founder of KP Acoustics Group. And today I'm going to take you through a journey of acoustics. And hopefully, by the end, we will see together the value of acoustics, mainly in commercial and working environments. So a few things about us. We have been in the market for some time. We are a group of companies. KP Acoustics effectively is the acoustic consultancy branch of our group, working throughout all architectural stages of a project, from concept and planning through to design with a whole design team and up to the final commissioning. Then we have KP Monitoring, which is effectively the branch of our group which deals with environmental monitoring, predominantly noise and vibration, but we also cover air quality, indoor air quality, dust monitoring, structural monitoring. Then where the magic happens is KP Acoustics Research Labs, which is the branch of our group that deals with three areas. One is education, so we provide accredited courses for acoustics. Then we deal with R&D, which means that we cover effectively, we assist teams to bring together ideas into reality through R&D by putting teams together, research teams together. And the third one is acoustic product testing. So we have a fantastic facility in Southampton, in the south of England, where we can test acoustic products for their sound insulation properties in a transmission suite, as well as in an anechoic chamber. Finally, NView, what you see there is effectively our very smart monitoring system, which we have developed in-house and has been a paradigm shift in the area of environmental monitoring. Now, let's go to our first chapter, Introduction to Acoustics. Now, very basic things for everyone to understand. What is sound? Sound is a disturbance that propagates through a medium. So effectively, if we had a magic camera that we could see how my voice moves into the air, more or less that's what we would see in 3D, of course. Of course, as humans, the medium by which the audible waves are transmitted is effectively air. So we have the air molecules moving, doing this effectively. Now, what is absorption and reflection? So as a wave, as a sound wave, again, if we take my voice into an enclosed space like my office at the moment. So as a sound wave strikes a partition, we have the incident sound. Then some of this energy is absorbed within the partition, within the wall or the floor. It's converted into heat. Of course, we don't feel the heat. It's infinitesimally small, but that's how thermodynamics work. Then some of this will be reflected. And of course, some of this energy, whatever has moved through the wall, some of this energy will be transmitted. So the amount of energy which is transmitted is dependent on the material and the construction of the partition. And as we said, the remaining energy, i.e. that which is not absorbed or transmitted, is reflected back into the space. Now, sound energy in a room behaves in a similar way to a water tank with an inlet and an outlet. The water flowing in is the equivalent to the sound source feeding sound energy, sound power into the room. The leak is the equivalent to the effect of absorption or transmission that we saw earlier. If the leak is greater than the input, the water volume in the tank will reduce over time. And on an opposite note, if the input is greater than the water level will increase. In a room, if a sound source, if a sound source can provide a power which is higher than the absorption, the sound pressure will increase. That's what we see in spaces which are very, very reflective. If there is a constant input of sounds, then practically speaking, the sound is amplified and doesn't die out. Now, what you see there as the red line is a growth of decay of the amount of water in the tank. So a room with very high absorption will have a lower level of sound because all the sound is absorbed. The acoustic energy is absorbed. So once the sound is stopped, the sound energy in the room will decrease more slowly than in a room with high absorption. Now, this is what we see when a sound is generated. It creates reflections. We have the first strong reflections, and then we have the smaller reflections. Now, what you see there as the red line is the initial impulse. So there's a concept there to discuss, which is reverberation. Reverberation is measured by the time that it takes from a sound stopping to lose enough energy to completely disappear. As different listeners have different sensitivities to a standard, to sound, sorry, then we must find an objective standard, and that is what we call as RT60, i.e. reverberation time 60, and 60 means that it is the time for a sound to decrease to a millionth of the original amplitude, i.e. 60 dB. Effectively, it's the time it takes for the sound to completely dissipate, to completely disappear. And that was derived many, many years ago from measurements within a concert hall. So, as we said, the direct sound is the initial impulse. Then we have the first strong early reflections, which start building up and create this reverberation, this echo, if you want to call it. Now, we as humans are used to hear a sound that has a mix of direct, indirect, and reverberant sounds. And the way we hear humans is important because this mix of the three types of sounds gives us information regarding the distance from the sound source, the location of the sound source. That's how humans hear. A sound, for example, with high direct sound will sound very close by. A sound with high reverberant component will sound more distant. And again, this is exactly what we said earlier about the sound that it takes for it to pretty much die out. So if the original sound was 100 dB, by the time it has reduced by 60 dB, i.e. RT60, that's the actual identity of the space. Now, we move to a concept about sound insulation. So if we have a sound that is initially transmitted through the air, this is what we call an airborne sound source. This includes exterior noise, such as traffic, aircraft, or weather noise. But it also includes interior noise, such as people talking, televisions, music played back through our hi-fi, telephones, building services, a number of things. So when the sound strikes the surface of a partition, then, as we said earlier, some of it will be reflected back into the same space, but some of it will transmit. So this is what we call direct sound transmission. Now, the level difference between the two, so whatever is the original sound, L1, level 1, minus level 2 will give us a very practical indication. This difference will give us a very practical indication of the performance of the partition. There are a number of different methods of measurements and associated values of assessing the airborne sound insulation performance of a partition. In the UK, we have R, capital R with a subscript W. But we also have, which is a laboratory-based metric, but we also have an in situ based metric, which is called DNTW. And again, similar in the States, United States, we have the STC rating, which is mainly States and Canada. So this is similar, but not equivalent to the RW, as it's 4 to 6 dB higher. So this is effectively, these are the values. The RW, going back to the UK, is what we see in specification books, like, for example, White Book. Then we move to footfall noise, impact and structurally transmitted sound. One of the most common noise and vibration problems in multi-story buildings is the transmission of noise directly through the structure of the building. So this is due to impact noise from footfall, vibrations from, for example, plant and machinery, floor deflection, which is normal, especially in houses where they have timber joists, all timber joists, or, for example, vibrations from a gym. That's a very hot topic at the moment in the UK. So gyms being effectively placed in higher floors than the basement or ground floor, and they create vibrations. So the vibration of the floor causes the attached structures to vibrate as well, forming flanking paths, what we see there as the yellow lines. So this vibration re-radiates as sounds in other building spaces, including rooms below or next to our space. And that's what we experience as impacts, as re-radiated structure-borne sounds. In most buildings, the most common cause of structural noise is impact on the floor, i.e. Footfall noise from our neighbors upstairs. And this is tested as part of the building regulations requirements. And we move to a concept which is very, very important in acoustic design, called flanking. So flanking, you need to think water, you need to think sound as water. It will find the easiest way to travel. So when we're talking about flanking paths, they are effectively all the weak paths that sound can find and transfer into adjacent spaces. And that's why it's very, very important to engage with an acoustic consultant at early stages so that we can have a look at all these individual details, because there can be a really, really high budgetary allocation on building fantastic partitions, very, very high performing partitions. But if the flanking, the junction detailing, i.e. how the partition meets the ceiling or the floor, if they're not reviewed early, then we may have problems. One very, very important detail to note is that when we test, what we said earlier, when we test the performance of partitions in laboratories, the conditions there are pretty much flanking free. So there is minimal, if not zero, flanking. This means that laboratory insulation values, this RW or the STC that we discussed earlier, will rarely be achieved in situ. For this reason, it is common to apply let's say, a penalty, okay, which can be anything from 10, 8, best case scenario, up to 12, 14 dB, in order to bring the laboratory value down to a real life scenario. Now, let's move to our next chapter of office acoustics. Now, acoustics play a crucial role in design, influencing well-being, productivity, and privacy. This section will introduce the importance of acoustics in various spaces, focusing on the impact of flooring on acoustic comfort. Now, health and well-being. Well-being is a very, very important concept, which is, especially since COVID, it has strengthened. It has strengthened in the market. Noise, whether we want it or not, is a major pollutant and the second highest environmental cause of illness in Europe for sure, but maybe in the world. Noise exposure creates fatigue, and our bodies react to noise with physiological reactions, such as increased levels of cortisol, elevated heart rate. Now, exposure to high levels of environmental noise is well documented, and you're looking at a number of issues associated with this, from mental health, cognition problems, to even, believe it or not, delay in healing in hospitals. So when patients are exposed to noisy environments, they do not heal as quickly as if they were in a quiet environment. Noise also has a strong effect on learning and focus. High levels of background noise in school classrooms have been linked to higher increases in stress-related factors, such as stress, hyperactivity, inattention, and behavioral issues. So, this is definitely a concept that we need to have in mind when we design buildings. Now, reverberation. Reverberation is a key factor in the acoustic design of buildings. Reverberation is more or less what I would say is the acoustic passport of a space. It has other values, other metrics as well to measure, but the main subjective metric of a space is reverberation. It's the first thing that we will notice when we enter a space. Now, controlling excess, or I shouldn't say excess, maybe high reverberation time is crucial for achieving optimal acoustics in different types of spaces, such as classrooms, offices, auditoriums. It can impact for sure sound quality, privacy, and noise levels. So optimizing reverberation time in building promotes for sure better acoustic environments, aligning with British building guidelines and legislation. A key acoustic challenge, of course, throughout this design exercise is the balance between keeping the visual aspects while managing the acoustic performance. And that is always, I wouldn't say a conflict, but it's always a challenge between members of the design team. Now, every space has a different acoustic identity. It has a different use, and we shouldn't be designing, for example, recording studio to sound like a multi-use space and vice versa. That's why bespoke design is very important. The materials, size, and structure of a building will have a significant impact. What we just heard is a parking lot. So a car park underneath an office or an apartment block will have very reflective surfaces and therefore long reverberation, which you just heard. Then, a very simple auditorium in a school, for example, what we see here, need to have a sufficiently low reverberation for speech to be intelligible, whether it's natural or amplified speech. But for example, in other cases, they may need a long enough reverberation for music or performance to be engaging. Then we go to medium or small rooms. The majority of absorption comes from sound striking a surface. So as rooms start getting smaller, reverberation tends to decrease. And of course, domestic rooms, what we just heard, such as living rooms and bedrooms, have traditionally low reverberation time. The underlying point here is that every space has its own acoustic identity, and that's how it should be treated from the outset of the design process. Now, another very, very important concept is speech intelligibility. Effectively, intelligibility is the ability to understand connected speech. It is particularly critical in spaces designed for education or performance, but it is also important in healthcare settings and public spaces, mainly for safety and information announcements. Intelligibility is affected by three main things. One is the background noise. Simply, if background noise is high, it is difficult to separate speech from background noise. Second is reverberation time. So a very long reverberation time, i.e. a very echoey space, causes sounds to overlap each other, making speech muddy and indistinct. And the third one is the signal to noise ratio. This is the level of the signal, which is the speech, above the background noise. So again, if the noise is high, in order to achieve a good signal to noise ratio, the speaker needs to raise his or her voice or require amplification. A measure of how well sound is understood between locations or people, again, is speech intelligibility. And what we call STI, Speech Transmission Index, is the most common measure of quality between spaces. STI expresses the ability of a communication channel to carry across the information. It is an indirect, of course, measure of intelligibility, as it predicts how many systems or rooms affect this transmission channel, the intelligibility of speech, and is measured using a very special test signal with speech-like characteristics. And effectively, it varies from 0, which means completely unintelligible. We don't understand anything of what our fellow speaker talks about, to 1, which is perfect intelligibility. Now, another very important concept is privacy. Privacy effectively is the opposite of intelligibility. It's the ability to not understand speech. And that's very important in settings like office environments, where effectively we have meeting rooms or boardrooms where very important points are being discussed, and no one must hear anything from adjacent spaces or from the open plan spaces. As we said, examples are offices, residential buildings. Within homes, good acoustic design ensures that noise from external sources is minimal, preserving the quietness and privacy of personal space. Hospitals is another area where privacy is important. Mainly, it's critical for patient comfort and confidentiality. In schools, also in an educational setting, proper acoustic privacy can prevent classroom noise from disrupting adjacent spaces, such as classes or admin areas. And courtrooms. In legal settings, acoustic privacy is essential to maintain the confidentiality of discussions among legal professionals. Again, there are different documents in the UK. We have building regulations for residential. We have British standards 8233, which covers a broad range of spaces. We have health technical memorandum 0801 for healthcare spaces. And again, some means of assessing acoustic privacy is a speech privacy assessment. So either through the STI we said earlier, or the articulation index. And again, speech privacy. Again, it's a very simple chart here, which talks about subjectively what we can or cannot hear, and it ranges from 0 to 1. So it's a key requirement in office spaces when we get involved, especially with banking, insurance, and healthcare, clients, where effectively we try to translate, speech privacy into a more subjective setting. And we always ask the client, do you mind hearing a bit of speech? And then they start, opening up and they say, we are okay if we hear some speech, but it needs to be muddled. We don't want to hear details. So we take this and we translate it into a specification for a partition. Now, as we said, acoustics play a crucial role in every environment, but every environment is different to each other. So there has to be an element of bespoke acoustic advice for each project, and that's what we're going to talk about here. Now, office acoustics, mainly because we want to bring the discussion to converge into the office environment. A common issue is noise from other room users, as well as the overall increase in levels caused by reflection. Now, there are some simple fixes for this. First of all, we need to understand that it's impossible to stop all of those noises. But a significant reduction can be achieved by using absorption, i.e. having an absorptive material mainly above the center point between the users and also on side and rear walls. So absorption is number one in terms of the solution we provide. Number two is blocking direct sounds, which can be done fairly effectively using acoustic screens. So that's a situation, that's the original situation, what you see here on the schematic of direct and reflected sounds, what we discussed earlier. So number one is the blocking of the main strong transmission path. Some of it will transmit, but most of it will be absorbed. Now, these can be very simple, MDF panels, and we can also incorporate some absorptive material so that it further improves its performance. The second is, as we said, applying absorption, and that can be panels on the ceiling, on the walls, and of course carpet. Carpet is the best absorptive treatment that can be applied as a uniform layer. And the beauty of carpet is that we don't see it because it's subconsciously, it's always there. But it's a very, very good broad absorber. So, if we can have carpet, then great. Finally, as you see here, we have the same paths, but this time they are attenuated. And finally, we can have some masking noise. Maybe you have come across this concept of masking noise in offices. It's effectively a technology that is used to raise the background noise and cover all other sounds. While this may seem a bit strange, a bit counterintuitive, we're adding sound to cover sound, a very small increase in the sound level is noticeable, such as a phone ringing or a quiet conversation. But if the background sound level is higher, the distracting sounds will be less clear and therefore cause less intrusion. That's how our hearing works. Now, this is a chart that is really, really useful, which shows effectively the relation of a partition performance, which is the y-axis, versus the level in the receiving room. NR stands for noise rating. So effectively, this tells us that for a normal range of office noise levels, which is between 30 or 40 NR, for sake of argument, we'll call it decibels. We only, for a good privacy, we only need to go up to the zone of, let's say, 50 dB sound reduction of a partition. However, and that's why we always say that some noise, some background noise has to exist. If the background noise in an office is very low, so what you see, the y-axis going left, this means that in order to achieve a very, very high privacy, in order to not being able to hear anything from the office next door, we need to design very, very high performing partitions, which is logical if you think about it. It's what we said earlier. Some background noise is good, okay, because it blends with the receiving, the receiving noise. If our space is very quiet, we're bound to hear much more information. That's why we need to increase the performance of our partitions. On a completely different, the other range of the spectrum, if our office is very noisy, okay, this means that our partition, our separating partition, only needs to present a fairly nominal performance in order for us to, not hear, adjacent conversations. This is very useful because it helps us with the budget. It helps us translate the client's needs to a specification. Screening. Now, acoustic screens play a crucial role in managing noise. They can provide some privacy in open plan offices where employees often engage in phone calls or conversations. They can reduce the propagation of noise from equipment like reprographic areas like printers, computers, or even air conditioning units. In a call center where noise levels can be particularly high, acoustic screens can be used to limit sound bleed, sound transfer between workstations, what we said earlier. They can also be used to divide, of course, larger spaces into smaller ones. When it comes to materials, acoustic screens are usually made from sound absorbing materials. We can have, of course, glass partitions, what we see here, but we can have acoustic foam, we can have fabric acoustic panels, or perforated wood or metal panels. Absorptive treatments, again, we covered this in the theory earlier. This is the most typical mitigation for poor room acoustics. So by absorbing effectively acoustic energy in the room, we are able to reduce the level of reflections, i.e. the reflective, the reverberant field, and therefore the level of reverberation. Now, what these are comprised of? Now, they can be acoustic foam, they can be panels, they can be baffles. Acoustic foam is a fairly lightweight material. We can have fiberglass panels. However, there is now a wide variety of sustainability is a key element in product design nowadays. So there's a wide variety of sustainable alternatives, including wood wool, cork, sheep's wool, recycled plastic. For example, we have cork. Okay, cork is a renewable material that offers good sound absorption properties. It's also resistant to moisture and mold, making it a good choice for a variety of environments. We can have recycled rubber. This is mainly not so much for absorption, but for impact sounds. We can have hemp, acoustic panels made out of hemp. It's a fast-growing, sustainable material, and panels are made from hemp fibers. We can have mycelium panels. Mycelium, these are made from the root structure of mushrooms, believe it or not, and agricultural waste. So as they grow, the mycelium fibers bind the waste materials together, forming lightweight, biodegradable panels. We can have recycled denim. So our jeans, our blue jeans, basically, they're recycled. They are formed into panels and they are sold as acoustic absorptive panels. And of course, we have wool, actual sheep's wool panels. Natural wool is another renewable source that can be used in acoustic panels. It offers pretty good absorption and also contributes to thermal insulation. We have done some tests in our lab and the results are quite interesting. And again, what we said earlier about the direct sounds, which forms the direct and reflected sound, which forms the reverberant field, and how this is suppressed using absorption. Now, let's move to the next chapter, which is effectively the role of flooring in office acoustics. Now, flooring and especially carpets is a multi-role design element. Now, the first aspect, the first role that it provides is that it absorbs footfall noise. So it can be actual footfall, movement from people moving. chair movements, and other impact-related sounds that would otherwise be amplified by hard flooring. Carpet acts as a natural sound absorber. Remember, when we do design, it is not the small changes that that reduce the overall reverberation time. It is large changes. So in an office environment, if someone comes and says, "Oh, I would like a panel of 2 square meters," it it won't do anything tangible. However, having a large distributed area like carpets will create a subjective difference in the acoustics of a space. Of course, carpets with higher acoustic absorption, especially those with thicker padding, will help absorb airborne noise such as conversations and typing sounds. The result of that is that carpets will limit sound propagation, making conversations more private and reducing unwanted distractions. Offices with carpeted floors tend to have a quieter and more controlled sound environment compared to those with hard surfaces like tile, wood, or concrete. This contributes to better concentration, productivity, and general well-being. While carpet is effective, of course, in reducing noise, it works best in combination with other acoustic elements like what we said, ceiling panels, wall treatments, and furniture designed for sound absorption. Now, a bit of my futuristic self with some ideas on how I personally see innovation in acoustic flooring and carpets. The first thing that I see happening is carpet with embedded sensors. Future carpets, it's not so much future, things are already started happening, may include IoT, Internet of Things enabled sensors that monitor, for example, noise levels, occupancy, and foot traffic. Then we could have hybrid materials combining traditional fibers with acoustic foams or aerogels to create an effective all-encompassing element that can be applied into a room. Then we could see eco-friendly fibers. Biodegradable and recycled materials will become more common as the years pass by, offering high-performance acoustics with minimal environmental impact. And then we could even see carpets nano coating. So carpets with self-cleaning or antibacterial surfaces will help maintain hygiene in the shared workspaces. We could even see air purifying carpets. Some future carpets may actively filter and neutralize airborne pollutants, improving indoor air quality. Some case studies, just 3, where we were involved and where we didn't have the luxury of adding absorption on walls or ceilings, and where effectively carpet proved to be the main solution. One was in Electronic Arts, Guildford, where they had a very good number of meeting rooms, as well as demo for games, demonstration spaces. And they wanted an environment that was not highly reverberant. So carpet proved to be a very good solution. And then the other 2 was financial and banking and fintech companies in London, where effectively we applied carpet as a distributed solution to reduce reverberation. Tips for collaboration, again, seen from our angle as acoustic consultants. Engage early. There's nothing worse for a project and for a budget of a project to not involve acoustics from the outset, or an acoustician, I should say, from the outset. Forget about it and then come down the timeline of a project and think that, oops, we forgot acoustics. That will add significant budget to a project. If we are engaged early, then we can work with the whole design team, choose materials, choose build-ups, and provide a completely bespoke solution to fit the client's needs. Clear communication. open lines of communication to ensure that all parties understand acoustic goals, specifications, pros and cons. And of course, regular feedback. There has to be feedback sessions between designers to refine acoustic, choices for flooring or other materials in order to meet the acoustic objectives of the project. So, in conclusion for today's webinar, we talked about the importance of acoustic performance, especially when it comes to flooring. A well-chosen, good, sound as an adjective, flooring material as a carpet will will have a very, very strong impact on the well-being and productivity in various environments such as offices and homes. Again, regarding well-being, choosing appropriate flooring can reduce the overall noise levels and create a more peaceful environment. And we also touched upon the future of design with some ideas that are already happening in the market. So I'd like to thank you. Amandine, over to you.
Thank you so much for the webinar. Very interesting to see how we can optimize our workplaces in terms of acoustics. We have some time for questions, so if you have questions, you can ask them via the Q&A button on the top of your screen. Maybe first question, what are some emerging trends in office acoustics that architects and designers should be aware of?
I think that that's an interesting question. I think that we are at a point where technology will blend with the traditional materials like flooring, carpets, or plasterboards, and I think that immersive soundscaping, will enhance office environments. So we will be talking about having zones for happiness, zones for productivity, or choosing individual sounds that will create and induce different work modes, let's say.
Yeah.
So I think that except a very, very well designed space from an architectural point of view, technology will play a crucial role in enhancing all this.
Yeah, yeah. Indeed. Another question, what are some common mistakes companies make when trying to improve acoustics?
Well, that can be that's really good. That can entail a whole host of solutions. We have seen carpets introduced into walls, okay, as the contractor thought that putting a carpet between two layers of plasterboard will enhance the partition. We have seen resilient layers for footfall noise built into walls as well for no reason at all. The list goes on and on. Yeah, it's impressive on how bad materials can be used, but that's not the point. The point is that if we engage with an acoustic consultant from the outset, then all these mistakes, and of course the budget allocated to those mistakes in rectifying them, will be completely gone.
Yeah, yeah. Okay, thank you. Maybe one last question. It's related to technology. Do you use AI in your work if you are designing for offices? If so, how do you use it?
Yeah, AI has started with a bang, and the more and it is a big bang, of course, but the more we see it as a functional hyphen operational accelerator, not a replacement. Yes, it can accelerate, for example, data analysis. It can accelerate, for example, the acoustic modeling of spaces. It can help with the oralization of spaces. Oralization meaning create a software model and listening to a space, which is something we do, listening to a space before it's even built. However, I don't think the AI would replace the experience of an acoustic consultant, in the sense that I don't think it will be a magic black box that the architects can feed the drawings in and it can spit out, do this, do that, in order not to have flanking sound. It's very it's pragmatically difficult. So it will be for sure it is already an accelerator, and it will become even more so, but up to a level, and some human intervention will be needed.
Okay, that's clear. Thank you. Thank you for the talk of today. All details will be sent to you via email together with the recorded version and the Q&A. If you have questions specifically for Kyriakos, or if you want to have acoustic advice, I think you can visit the website KP Acoustics, and then I'll have a look at Kyriakos, kpacoustics.com or
.com.
Yes, perfect. Next webinar is the second one about acoustic flooring solutions in hospitality venues with Daniel Verloven, and Daniel will guide us through innovative solutions designed to deliver sound harmony in hospitality spaces. So thanks a lot, and see you on the next webinar.
Thank you so much.